All right, so now we are going to add in, like I said, an additional velocity because we're doing conservation of linear momentum. Now, linear momentum basically means that capital B is equal to m times our velocity. All right. Now, the hard part about this is that this is a vector, right? It has direction. We don't care necessarily about our capital B. We care about our lowercase b because that's what we plug into this equation right here. And in that case, our linear momentum per unit mass, because that's what our little b is then equal to our velocity, right? But we're going to do something, again, we're going to do it different than the book does a little bit. We're going to call this v, x, y, z. Because we want to remind ourselves that this is our velocity relative to our coordinate system, not our control volume. So, yeah, coordinate system. Always our coordinate system. Great. So when we plug then, remember this is our Reynolds Transport Theorem equation. When we plug in our capital B and our V, what we find out is that our change in rho, or sorry, not change in rho, change in momentum with respect to time, our total derivative of that is equal to the sum of all of our forces on our system, which is equal to d dt of the integral of rho v xyz dv plus the integral over our control system. Sorry, this is a control volume over here. The first integral is always over a control volume. Second integral, which is the integral over our control system of rho v xyz times w dot n hat dA. So if we were to now describe these components in terms of what they are, obviously this part here is the sum of all of the forces on our system. This part is the rate of change of momentum within our control volume. Let's write that out. Momentum within our CV. Okay. This is a tricky thing. Because we have a lot of decisions we can make about where we put our coordinate system, about how we measure our velocity, right? Most of the time, we're going to measure our velocity for our momentum the same way we measure our velocity for W, which is relative to our control volume, because we're going to put our coordinate system with our control volume, and they're going to move at the same velocity. And that really simplifies things a lot. Usually. Sometimes it doesn't. We're going to show the difference between pinning your coordinate system to your control volume and not in a little bit. But for example, if you have a tank of water that is in, like, let's think back to that hot tub in a stretch limo. If you have that hot tub of water that's traveling at 10 meters per second down the road, if you're measuring the velocity of that water relative to the car, it has no momentum, right? So this would be 0. If you're measuring that velocity of that water relative to, say, the road, which is stationary, well, it's not stationary because it's moving around the sun, which is moving around our what's it called? Galaxy, which itself is moving around a lot of places. So nothing's really stationary. But from our perspective, the road seems stationary, in which case we would have a non-zero velocity here, in which case this quantity would not be 0. So choosing how we pin our coordinate system is an additional choice we can make, because before, right, drawing our control volume was a choice we'd make. Now we can draw how we draw our control volume, and where we put our coordinate system matters a tremendous amount. It also matters for this part, which is the rate at which, by the way, I'm talking about the integral over the control surface, the second integral. This is the rate at which the momentum crosses the surface. It could be positive, it could be negative, and it's whether or not it's positive or negative is not solely dependent upon the direction that the fluid goes in, because now we have an additional velocity that can have a positive or negative value. Okay, so now we have, like I said, I kind of hinted at this, but let's say it explicitly. We have all the same tricks as conservation of mass. Plus 1, we can choose where to put x, y, z, which allows us, like I said, to sometimes get rid of this control volume integral here, because volume integrals, which we take the partial with respect to time of, can be very nasty if we're not careful. And 2, this is a vector equation, so when we do some of our forces, we pick a direction, and we only sum forces along that direction. It could be x, y, or z. It actually could be in an arbitrary angle, right? It can be an arbitrary direction. It doesn't have to be lined up with your coordinate system, but you're only ever summing the forces in one direction, just like you would for what's it called? Sum of the forces equal to mass times acceleration. All right, so let's see how this works. Every year I do this example, and every year I hope that we don't have an example from the previous year to say, look, people still use water jets, but they still use them. This year there was a discussion about using them in Portland, but they didn't. They've used them sparingly in America for the most part, and that's largely because I think because we have a robust libel system, legal system here, where if you get injured, it costs a lot of money. And as we will see, water jets have a tremendous potential to injure you. They were used in the that pipeline protest in, I think it was South Dakota, but they were mostly used there to soak the protesters. So they were spraying them with water. They weren't actually using them to push them over because it was cold there, and they were just trying to get them, which is not necessarily better, but they're trying to get them cold and therefore to leave. Okay, so we're going to neglect viscous effects. We're going to assume the water is evenly split, and we're going to ask a question of what requires less force to resist this water jet. 1, if you stand there and allow the water jet to hit you in the chest, where it splits in half and goes one in one way and one half in the other way. Or really, if you think about it, one half one way, one half the other way. Or if you were to put your arms in a triangle in front of you and split the jet in half again, but now your arms are at a 45-degree angle, and the jet leaves, instead of leaving vertically on the page, it leaves at a 45-degree angle. Okay, so we're going to, what model relates forces, velocities, and areas? Well, we only have one that relates forces at all, and that's conservation of linear momentum. So we're going to use conservation of linear momentum, and let's write it out. It says that the sum of our forces is equal to d dt of integral over control volume of rho v xyz dv plus integral over control surface of rho v xyz w dot n hat dA. And here you can kind of, so now we have, to some decisions to make. Let's make them. Remember, now that we're using conservation of linear momentum, it matters a lot where we put our coordinate system and our control volume. I'm going to put our coordinate system right on our person, where X and Y are in those directions and Z is coming out of the page. I'm going to draw my control volume around my person like this. And I'm going to do the exact same thing for this the second person with the triangle arms here. X, Y, Z. And I'm going to draw my control volume so that the fluid is leaving perpendicular to it and entering perpendicular to it. And on both of these cases, I'm going to draw a force in here, which is the force, I'm going to call it just F, but it's the force that the person is exerting in order to maintain their position. Okay, and I'm drawing it in the positive direction. I know that the force is actually going to be facing in the negative X direction because it's got to resist all this water, but I draw it in the positive direction simply because then I know if I get a negative value for my force, I just have to switch it. Trust in the process, right? Don't try to get there any faster than would be prudent, I guess. So we're going to assume some stuff. Our old friend, rho is equal to a constant. We're going to assume these people have stood here for a bit, so that's going to be A. B is going to be steady state. Although, if you ever watch videos of this, they often wiggle the jet, if you will, so that you can't adjust to limit the force on any one part of your body. So C is uniform flow. We're going to assume the jet is uniform in velocity when it crosses and leaves anytime it crosses our control volume surface. Great. So we got to pick a direction now, and I'm going to choose the X direction. So if this is 1, 2, we're going to pick now the X direction, and the sum of our forces, we're not a vector here anymore, the sum of our forces in the X direction is going to be equal to F, which is going to be equal to, and now we see the power of choosing our control volume and coordinate system the way they are. This first integral here, d dt of rho, integral of rho v dv, if we look at our control volumes, we have fluid moving through our control volume. It's true, our v is not equal to 0, but the amount of fluid and its velocity are not changing with time. So as a result, this is equal to 0. That is equal to 0 because of our steady state mostly. We've assumed steady state, which means fluid is not accumulating in our control volume. Therefore, we can make that equal to 0. And since we've assumed uniform flow and density is equal to a constant, our integral here goes away, and instead now we have to worry about each individual entrance and exit. So let's worry about case A. We'll call this guy A first over here. We're going to worry about A first, and let's look at these entrances and exits. So I have 1. Oh, shoot, I don't want to circle those because circles are just for our equations. 1, 2, and 3 for our entrances and exits. We have 3 entrances and exits. We have to have 3 different components, 3 different parts to our equation here. So let's do our entrance. We have rho of our fluid times now the velocity relative to our coordinate system of our jet, because we're worried about v, x, y, z now, is going to be actually 22 meters per second, but it's just going to be v jet, and that's positive because it's in the positive direction, okay? Because we're worried about momentum, right? There's no dot product or anything when we're worried about v, x, y, z. W dot n hat does have a dot product. We've drawn our control volume so it's perpendicular to our flow, so it's going to be positive or negative times the velocity. In this case, we have fluid entering our control volume, so it's going to be a negative times its velocity. So this is equal to a negative v jet. And then we have got rid of our We got rid of our integral, so now we just multiply by the area. And our area is actually going to be equal to Q jet divided by V jet. So you'll notice, by the way, that these two V jets will cancel out, and we'll just get Q jet. So we don't actually need to know the area if we know the flow rate. All right, so area 2, we have plus. Now we worry about the, again, sorry, this is the x component of our velocity, but our fluid is leaving our control volume at 2 completely in the y direction. So we have rho times 0 times, and it's leaving at the same velocity, so the dot product would be v jet, and then our area would be q jet over v jet times 2, or divided by 2. But we didn't actually have to write all that out, because we knew that our term was going to be equal to 0 because it has 0x momentum. Remember, we worried about all the momentum in a single direction. And so if it's leaving in the y direction completely, then we don't care about it. 3. Okay, so, and then area 3, not circled, area 3 is going to be the same thing. Rho times 0 times v jet times q jet over v jet 2. Wonderful. So these are both 0, and so we can just solve for our f, because we know we can cancel those out, and we know everything else, and we can solve for f. And we find out that our f for part A is equal to 330 newtons. Great. Now if we do part B, which is the person with the triangle arms, we're again going to pick the x direction, because that is the direction that this person is likely going to have to spend all of their force to resist this. And what we find out is we have an F, sum of our forces in the x direction is equal to F, again, because we just wrote that in here. We wrote that F in. And that's going to be equal to d dt of the integral over our control volume of rho vxy, or vx dv. Now, remember, again, this is equal to 0 because we are in steady state condition. We don't have any fluid accumulating with, we don't have any momentum accumulating in our control volume, right? So that's going to be equal to 0. Plus, our integral now, again, goes away for our second integral, because we've assumed steady state and uniform, and we have to take into account now each of our entrances and exits. So we're going to do 1 again, 2, and 3, going clockwise around, starting with the entrance jet as 1. And that 1, entrance 1, is going to have a, again, it's going to be the exact same as before. We have a rho, a v jet, times a negative v jet. And that first v jet is the vx, right, the x component of our jet entering our control volume relative to our coordinate system. And the second velocity is the velocity of the jet relative to our control volume dotted into the control volume normal. Ugh, it's a lot. But this one is negative, and multiplied times an area. But again, our area is just q jet over v jet divided by 2. Sorry, not divided by 2, because it's the whole jet. You'll notice, again, I've said this before, but I'll say it again. I like to write the sign of each of these velocities in parentheses, because sometimes our v jet is going to be negative, and our dot product will end up being negative, and keeping track of those negatives is easy. Let's be clear, it's not that hard. 95% of the time you're going to get it right, but there's no reason to miss a point when you don't have to, right? And so if you do this, then you can come back through later and spend all of your attention on just getting canceling out all of the extra signs. All right, and we know now we have to take care of our other entrances and exits. So let's do it. So we're going to do 2. And we're going to see as we get something different now. We get rho times, and now the x component of our momentum for exit 2, which is the top exit, which is leaving at 45 degrees relative to the horizontal. We have our velocity there is v jet, but the x component is multiplied by the cosine of 45 degrees. And now we have to multiply that by the velocity of the fluid relative to our control volume surface, which is just v jet. It's leaving, so it's a positive dot product. Okay. And we multiply by the area, which is q jet over v jet divided by 2. Now, I want to point out a mistake that a lot of people make is they get in a hurry and they start, well, one, you can, if you look at the first term for our exit 1, you can see that it's rho v jet times negative v jet times q jet over v jet. So we can often write this as rho v squared times a, and they'll just do that. And they'll do that for this term here. They'll do v jet times the cosine of 45 squared, and that's not right because our w dot n hat is not multiplied by the cosine of 45, just our vx. Okay, so it's easy to make that mistake if you're in a hurry. 3, our surface 3, which is our bottom exit, is equal. We're going to have a rho times v jet, and again, now we need to take the x component, which means we multiply that by the cosine of 45. Cosine of 45. And we're going to multiply that by our w dot. And in this case, our fluid is leaving our control volume perpendicular to our control volume surface. So it's going to be a positive 1 times our velocity, which is v jet. And we multiply by the area again, which is q jet divided by v jet squared. And remember, the whole reason we can assume that our fluid leaves at the same velocity is because we're assuming it's inviscid. So if we don't have any viscous effects, there's nothing to slow it down, right? It's just going to keep its same momentum. Any kind of pressure will just change its direction. It will not change its velocity. Great. So now if we plug all of this stuff in, we see that our F is equal to 96 newtons. Sorry, these were both negative, which means they point in the negative direction. So what's really interesting here is that if we just take this jet without doing anything, it will produce a force of 33 newtons, which is approximately the weight of a 33 kilogram weight on you. Or, if another way to think about it, there's 2.2 pounds per kilogram, so somewhere around 75 pound child standing on your chest, right? And you don't think that's a lot, except for, have you ever had a child stand on your chest and it's just like digging with their heels? That's kind of what you're experiencing here, right? Because this jet has a relatively small diameter. And so it actually produces a tremendous amount of pressure where it hits. If it's not it'll cause bruising when it hits you in a major muscle, right? But if it hits you somewhere sensitive, like in your mouth, nose, eyes, ears, it can cause a tremendous amount of damage. You can imagine all of that force pushing on your eyes. Yeah. Also, imagine a 77-pound child drop kicking you or being thrown at your chest or something like that. It's going to knock you over, and that's tremendously dangerous. I don't know if you guys all remember during the protests that were occurring downtown, there was an elderly man that got knocked over by a policeman, just pushed over, right? And he was in the hospital for a month, I think, with a head injury because he hit his head when he hit the ground. He started bleeding like crazy. It was a horrible thing. The same thing happens with these water jets. It's very easy to knock somebody over with a water jet. And like I said, as much as we would like to be able to assume that we can put our hands in a nice triangle and deflect the flow, oftentimes they wiggle the jet around so that you can't adjust your body to minimize these forces. You're taking it full on for the most part. All right, so but I want to explicitly have you guys now describe to me in words why position B, triangle hands, has less force. Okay, so try to do that. Try to describe in words why position B has less force. Okay, I forgot that you guys could just pause the video. I'm going to assume you paused the video, and we're going to write down what the answer is here. And the answer is that the water leaving is carrying away some x momentum. All right, it's carrying away some x momentum in B, where in position A, where we just take the velocity straight onto our body, it's leaving in the y direction, which means it has no x momentum. Its velocity hasn't changed, it just has no x momentum, and that's all we care about is the x momentum. So if any time we can have the water leave with more x momentum, it's going to produce less force on us. So this equation only works, by the way, as long as we're in an inertial reference frame, i.e. my control volume and my xyz coordinate system cannot be accelerating. There is a variant of this equation where we use an accelerating coordinate system, but we don't cover that in this class. Okay, so in the next video we are going to describe why it's so important to choose where your coordinate system goes. We are going to look what happens if we have a person running away from this water jet in the winter. Maybe this is part of the South Dakota protest or something like that. So you have a winter jacket on, and that winter jacket is absorbing some water, and you're running away from the jet, and we can choose to either put our coordinate system on the ground or on the person. And we're going to do both of them, and we're going to see how much easier it is to put the coordinate system on the person and see that we'll get the same answer no matter what. Okay.